Hey everybody. For today's math video, we're going to return to the world of the practical, something you can actually use in your everyday life here. And we're going to talk about how interest is earned on money that is borrowed or lent. And to start, we explore the idea of what is interest, okay? Well, let's consider this situation. I'm very well off. I'm doing very well for myself. I've got a lot of money lying around. And you're not doing so well. That's all right. We all fall on hard times. But you've got this idea that's going to get you going off the ground. You got a business you want to start, and you just need some starter money. And you come to me and you say, hey, can you help me out? And I say, all right, what do you need? And you're like, I could really use $10,000. Whoa, big number, but not to me. Remember, I'm doing very well. And I say, all right, I'm going to loan you $10,000. Okay, great. So you've borrowed $10,000 from me. So let's start with definitions. The amount of money you borrowed from me is called the principal. We refer to that as P. Okay? And so in this case, we say the principal is $10,000. All right. So now, eventually, you're going to get your business off the ground, you're going to be pulling money in, and you're going to have more than $10,000. And so you're going to pay me that money back. So you give me my $10,000 back and all as well, right? Well, why am I so well off? Why am I doing so well? Is it because I have a job where they just like to throw money at me? Is it because I won the lottery? Not necessarily. We're going to go ahead and say it's because I am a shrewd businessman myself. I'm an investor. And so I see good opportunities when they're available, and I invest my money so that I get money back because of that. In the simplest terms, I put it into stocks and I earn dividends. The stocks grow, and so the value of each stock that I have grows as well. And then appropriately, I sell it off to someone else and make money by doing that. And so there's on average, a percentage to the amount of money that I invest that I get back. So for me to say that I've given you $10,000, and then 2, 3, 4, 5 years down the line, you give me that $10,000 back. That's not good enough. And here's my biggest reason why. During those 2, 3, 4, 5 years, I could have been investing that money and earning more money with that money. And so now I don't have any of that extra money, that interest as we call it. That's not mine to use. In fact, if you did your job right, it's yours to use. So I earned that $10,000, and then you got the extras that come with it due to investing, whereas I didn't. But it was my money to begin with. So to me, that's not fair. And so I'm going to say, you know what? I know how I use my money. I know how I invest, and I know the rate of return I tend to see with it. And so when you pay me back, you're going to owe me more than $10,000. There's a percentage to it that I'm going to add on. And you'll get to know that in advance, of course. But that's what's going to happen here. And so now we're going to start to define how do we calculate that percentage and how do we use that to calculate the interest. Well, first of all, interest is calculated as a percent, as we had said. And so we need to define a certain percent that I make in a certain amount of time. That's the key thing that often gets lost about percent. Percent is a rate. It's not, or interest is a rate. It's not just a percent, it's how much percent per a certain amount of time. Now, as human beings, we have decided that interest rates are going to be decided based on the calendar year. So per year, or per annum, you may hear it said, is how much interest do I earn. Now, for the sake of my math, I'm going to use a nice number to make it easier. It's a relatively high number, but let's say that's just how shrewd of a businessman I am. And I'm going to say I can earn interest at a rate of 10% per year. Okay? Well, we use R to denote the interest rate, and we say, here I'm saying that it is going to be 10% per year. Now, from now on, I'm not going to specify the per year each time because we accept that to be the way it is. It's just what we do as human beings. You can use any unit time you want as long as you're consistent. And then finally, I say, how much time do you have my money? So we call that T. And so however much time it's gone that you have the money, then when you give it back to me, I'm going to be putting that number in right here and into my formula, and that's how much additional money you're going to have to owe me because that's going to be the interest that I've earned. Okay, so how do we write this as a formula? Well, it's just a simple idea here. It's just a definition, okay? I say that the interest that I earn, I, is equal to the principal, what you originally borrowed, P, times the percentage rate, R, which is a percent per year, so how many years, times T. And this is what we call simple interest, or the simple interest formula, because it is so simple. And so we say, there we go. All right, so if you have my money for T years, I throw that in here using these values right here, and I get how much interest you owe me. So let's see what a couple of those look like. Okay, so for the examples, you may actually want to have a calculator out with you so you can kind of follow along. I'm going to be doing the math quickly here. I already have the answers so that we're not taking too much time. But if you need to justify any of these, pause the video, get out your calculator, and verify that what I'm showing you is true. All right, so we've got our simple interest formula here. I equals PRT. And we have here a chart in which on the left column I've got different T values. And remember, T is measured in years. And then in the right, we're going to be filling in P plus I. Remember, I is just how much interest I've earned, but how much money do you owe me back? That's really what matters to you the most. And so I'm going to be adding that back into the initial principal P. Because remember, you got to pay me back my $10,000, then plus whatever interest has been earned. All right, so to start, for 1, I'm going to plug in 10,000 times 0.1. Remember, 10% is the same as 0.1 times 1, which means, just leave it alone. So 10% times 0.1, well, that's 1,000. So I've earned $1,000 in interest. Add that to 10,000. In 1 year, if you kept my money for 1 year, you're going to owe me $11,000 at the end of that year. Okay? Do the same thing with year 2. Okay? 10,000 for P, 0.1 for R, now times 2 for T, and we get 2,000. That's how much interest is earned in 2 years. Add that to my initial principal of 10,000. If you keep my money for 2 years, after 2 years, you would owe me $12,000. Okay? Hopefully you can see this is a straightforward pattern. It's very linear, so I can very easily fill in this chart. After 3 years, the interest goes up by another $1,000. After 4 years, another $1,000. After 5 years, another $1,000, and so on. Okay? So again, if you kept my money for a total of 5 years, at the end of that 5 years, I expect to be given $15,000 and not $10,000. And that's simple interest, all right? Because remember, I said, based on my investment schemes, I expect my money to return 10% per year. And so without having this $10,000, I'm not able to see any of that money that I could have been making. And in fact, you could have been seeing that money. And so I'm going to ask for that back. Because it was money you borrowed from me, so whatever you generated from it had better be coming back to me. And if it wasn't enough, you better dig deep, because I'm going to be expecting all of it back. That might sound mean, but this is not about emotions. Take the emotions out of this, the fairness, the niceness, the forgiveness of loans, none of that here. It's just straight, logical, emotionless math. After 5 years, you pay me $15,000. Straight up. Okay? But is that, in and of itself, still completely fair? Let's think about this. In 5 years, how much money did I say I'm missing besides my initial $10,000? I said I'm missing $5,000. Or better yet, just go back to 1 year. In that 1 year, I'm missing $1,000. What could I be doing with that money? Well, again, I'm a shrewd businessman, so I'm probably going to be investing that money as well. So not only would my $10,000 be earning me 10% per year, but so would the $1,000 I made that first year. In subsequent years, it's going to make me 10% per year. And then whatever that earns, the next year, it's going to make me 10% per year. So now I'm looking at this and I'm thinking, what if you kept my money for 30 years? You'd owe me an additional $30,000, but what could I have been doing with that $30,000 during those 30 years? Now, that's an extreme example, but think about that. That's money that is mine, and I don't get to see, and I don't get to use, and I don't get to make money with. So to me, this isn't fair enough, and so we're going to introduce another concept here called a compounding period. Okay, so as a shrewd businessman, I'm saying that every year my money earns me 10% of what it was. And so I might say to myself, you know what? Every year I'm getting that money and then I'm going to turn around and reinvest it for the next year. So when I loan you this money, I would then say, here's the deal. Every year you have my money, I'm going to calculate the interest, and then I'm going to roll that interest back into the principal, And for the next year, I'm going to calculate the interest based on that new, larger principal amount. We call that compounding. I'm compounding the interest into the principal. And so for each year that you keep the money, the more interest gets compounded, which means the more interest I'm earning. But that's really fair once we think about it, because again, that's my money that I would have earned that I could have turned around and earned more money with. And so that's what we want to do with this. So we're going to start with the idea that it compounds once a year. And we usually say the number of compounding periods in a year, or in time t, is denoted by n. So we're going to start filling in this chart here for n equals 1. All right, so to see this in action, again, think about the first year. And in the first year, it's just the principal. It's just the $10,000. And at the end of that first year, that principal has earned, as we found here, $1,000 in interest. So I roll that back in, and I say you owe me $11,000. If you pay me after that year, then that's what you pay me. You pay me $11,000. But here is where it changes. Now, if you're going to wait one more year, you're going to go 2 years. For this next year, I'm not calculating it based on P equals 10. I'm updating P to this number right here, 11,000. And so I go to my formula over here, and I plug in 11,000 for P, 0.1 for R, and it's still one more year, so T is still 1. And then I say, how much interest is that? Add that back to the $11,000, and that's how much you would owe me after 2 years. And that turns out to be $12,100, which, again, should make sense. There was an extra $1,000 that you owed me after that first year. Well, 10% of 1,000 is 100, which means that $1,000 would have earned me an extra $100 in that year, and thus I should have $100 more than simple interest, which I do. Now, I've got an extra $1,100 that is going to be earning interest the next year into the third year. And so I'm going to calculate my interest for the third year based on this new updated principal of $12,100. And what I would get at the end of the third year, plugging it back into this formula, and then adding back into P, is $13,310, which again should make sense, because not only do I have an extra $1,000 in interest from my principal, but I have an extra $100 in interest from my first years of interest, and then I have an extra $100 of interest from my second year of interest, and then I have 10% of that, which would be $10. I've got an extra $10 of interest from my third year. So we can see by year 3, by compounding annually or once per year, I would have an additional $310 coming my way. And we can do the same thing for 4 and 5. I'll leave it to you to show that this is the case. But what you would have here is $14,641. And what you would have here is $16,000. Sorry, I already can't read. $105.10. If I could memorize all of that, I would be a genius. So yes, I am cheating. I have these written down. But I leave it to you to verify that I did my math correctly. So as we can already see, in 5 years' time, it's nice to have interest. You're paying me more than what I started with, but now my interest earned interest once a year, and I've increased from simple interest to compounding once per year. I increased my return by $1,105.10. So compounding makes sense, too, from a practical standpoint. And then, of course, as the lender, I definitely want to be doing that because I'm going to get more back. But remember, I'm doing this in a fair way. I'm saying that, honestly, I would have made this money had I been able to keep my initial $10,000. But why once a year? What if the investments that I do give me money back every 6 months? So twice a year, I see my interest returned. Well, how would that affect how much you would owe me? That's what we're going to look at next. So now we're going to see what happens if I earn interest twice a year on my investments. So for your loan to me, I'm going to compound my interest twice a year. That is n equals 2. All right. Well, let's start by just using the formula here. All right. So the very first 6 months, the first half year, I'm going to be plugging in here 10,000 for P times 0.1 for R. Now T This is where we want to be careful. We can often easily get N and T confused. N is how many times per year, so how much of a year has passed. Well, it's been half a year. So this is times 1/2 or 0.5. You can leave it as a fraction or a decimal, whatever works best for you. Now, if I multiply that through, I get 500, which intuitively should make sense. If in 1 year I made $1,000, in half a year I should make 500. Okay? But instead of letting that 500 just sit there for the rest of the half year, I'm going to roll that 500 back into my principal right away. So I'm not through 1 year yet. I'm only halfway there. And after half a year, you owe me $10,500. And that's true whether we're doing simple interest, compounding annually. It's going to be the same there because nothing has compounded at this point. But now I'm going to say, okay, for the second half of the year, the new principal is $10,500. My interest rate is still the same, and I'm going for another half a year. So I multiply that way. And what I get here is a little bit different. What I actually get here is 525. So during the second half of the year, I've earned $525 in interest. So I roll that back into this principal right here, $10,500, and after year 1, you would now owe me $25. So as you can see, by compounding more often, I'm showing an increase already. Originally, compounding annually, it was $11,000. Now I got an extra $25 in there. Well, $25 may not sound like a lot compared to $10,000, but it's the principle of the matter. It is more. It is more money. And that's money that I'm reinvesting from the start. So if you're keeping this money for much longer as you go through here, well, then you're going to find that it's going to keep growing. All right? Now, it's kind of tedious to go through all of this math each time, but it's good practice. So I actually encourage you to do that. If, in all seriousness, I know it sounds nerdy, but I do encourage you to do that. But I'm going to go ahead and show you what these totals are. As you go through and do the math, what you're going to find is how much you'll owe me after 2, 3, 4, and 5 years. So, after 2 years, $12,155.06. So now I've got an increase of $55.06. There's definitely going to be some rounding. When you do your math, make sure you save the rounding to the end. Okay? If there's fractions of pennies, they stay there until you're ready to write a number down. Keep those there as you continue to do the rest of the numbers, because that's actually how it's done in the real world, and mathematically it's how it should be done anyway. Okay? After 3 years, how much do you owe me? $13,400.96. Almost a $100 increase from compounding annually. Okay? After 4 years, how much do you owe me? We're up to $14,774.55. Definitely gone over the $100 from where we were before. And finally, after 5 years, we're at $16,288.95. So if nothing else, we maybe don't want to compare back to compounding annually. Maybe we compare back to simple interest. And the increase is very, very obvious. I've already increased it by $1,288.95. I've already increased it by more than 1 year's worth of interest on my original principal. So in 5 years, that's a lot. Think about that. That is a lot of money. I'm expecting this money to earn me $1,000 a year. And by compounding twice annually, I'm going to get an additional $1,000 in there. But that's what I would do with my money. And so I just expect you to do the same thing upon returning it to me. Now, going through and doing all of that math, even on a calculator, very, very tedious. And if you know anything about the financial world, you know that dividends in stocks are almost always paid out quarterly. That means once every 3 months, which means n equals 4. That means to get the value here for number 1, I have to do this method 4 times. And then to do it for year 2, I'd have to do it another 4 times. So 8 times total, 12, 16, 20. I don't want to do that. Nobody wants to do that. You don't even want to program a computer or a calculator to do that. There's got to be a better way. And that's what we're going to explore next. Is there a better way? And if so, okay. So we want to find a formula for calculating compound interest without having to calculate the interest at each of the compounding periods, because that can get very tedious very quickly. So to do that, we're going to define some new variables and some new ways of looking at our current variables. So first, we're going to define the variable a, and we're going to say a stands for the amount of money that has been accrued. So this is basically how much principal plus how much interest put together. Now this is going to be how much has been accrued at any given compounding period, so we're going to put a subscript on it, and we of course start with subscript 0, meaning at time 0 how much money is accrued. Well, that's like saying, okay, I loan you $10,000 and immediately you pay me $10,000 back. Well, then you owe me no interest. No time has passed, so a sub 0 is just the original principal amount, p. Okay? Next we're going to think about interest and how it's earned. So we're going to look at interest at any given time period. So again, we'll use capital I, but this time I'm going to put a subscript on it. I'm going to say at some time period k, or some compounding period k. And I'm going to say this is the interest earned on the principal, or more accurately, the amount of money accrued up to that point. Well, the amount of money accrued up to that point was how much money at the previous compounding period, so it's not k, but k minus 1. And I still multiply that by the rate. Okay, my interest rate hasn't changed, and it's still per time period t, but remember, this is for each compounding period. So if I have n compounding periods in 1 year, then each compounding period is of length 1/nth, 1 over n. So think about it this way. When I had 2 compounding periods in a year, I said that, well, that means every half year I'm earning interest. So my time was 1/2. And if I'm earning interest quarterly, that means 4 times a year, then I have to do this every 1/4 of a year. So my time is actually 1 over n each time. And n is a constant, and so I don't have to have any sort of subscripts there or anything like that. So there we go. So this is what we're going to use to find the compound interest formula. So let's start with the period a sub 1. So after the first compounding period, how much money do I have? Well, I start with how much money did I have previously? Well, that was the previous compounding period, a sub 0. And then I'm going to add to it how much interest that I earn during this compounding period. So during the first compounding period. All right. Now let's fill in what we know. We know a sub 0 is just p plus I sub 1. Well, that's going to be a sub 1 minus 1, which is a sub 0, which again is p, times r, which we know is still r, times 1 over n. You know what? As I take a look at this, I realize that this is r times 1 over n every single time. Those will never change. It's my a that's going to change. So I can actually simplify that even further. So up here, I'm going to change this to r over n. And I'm going to do that same thing right here just to make my life easier. The simpler I can make it, the happier I am. Mathematically, it's the exact same, but it's just a little nicer to write. Now I want to simplify this, and notice in both terms I have a p, so I can factor that p out into the front of the parentheses. So that p goes out front, and what's left over, well, when you divide by p, you're left with 1. And when you divide out p here, you're left with r over n. Okay? So at time 1, or at compounding time 1, I can calculate my amount accrued that way. All right? That's a nice formula, but how useful is it for other time periods? Let's find out. All right? I'll go a little further to the left here for this one. A sub 2. Well, again, it's the same in each case. I'm starting with the previously accrued amount, A sub 1, and I'm adding to it the amount of interest I accrue during the second compounding period. Okay? So fill in what we know. A sub 1, we just calculated that. That's that right there. So that's just P times 1 plus R over N plus I sub 2. So we're going to use this up here, plus I sub 2 is A sub K minus 1, so A sub 2 minus 1, that's A sub 1. Well, that's just this again, plus P times 1 plus R over N. That's the A sub 1, and then times R over N. Well, now that's getting pretty messy. Not too fond of what I'm seeing so far, but hopefully something stands out to you. Both of these terms have this value right here, P times 1 plus R over N. P times 1 plus R over N. So just like before, I can factor that out. So I factor that out, and I get that out front, P times 1 plus R over N, times, in parentheses, the leftovers. What are the leftovers? Well, I took everything out of here, so I'm left with 1 here, and I took everything but R over N out of here, plus R over N. Well, that certainly looks better, but I hope you can see we could make that even better. Notice how we've got the same thing being multiplied. When you multiply the same thing twice, all you're doing is squaring it. So this is really, I'll write that right here, P times 1 plus R over N squared. Oh, no, that's really nice. In fact, that's almost just as nice as this one right here. Compounding period 1, compounding period 2, all we do is add an exponent. I wonder if that pattern would hold. Well, to see if that pattern continues to hold, we're going to use a little something called induction. Okay, now we're going to test if the pattern we were observing earlier will hold true for every number that we need it to. And to do that, we use a method called induction. And with induction, we start with the idea. I'm pretty sure it looks like this. So we call that the claim. I claim that my formula for A sub k is going to be P times 1 plus R over N to the power of k. And then that this will be true for k greater than or equal to 1. Okay? Now, we have to prove by induction using 2 parts. The first part is show that it's true for some value of k, specifically the first value. Okay? So we let k equal 1. Plug it into this formula and see what we get. Okay? Then we have A sub 1 equals P times the quantity 1 plus R over N to the power of 1. Now, anything raised to the power of 1 is just itself, so we can actually erase that. And what we just found previously was that is the value of A sub 1, so we know it's true. Okay? So it's true for that value. Part 2 says, assume this is true for some value. Don't know what it is. Let's just let it be k equals j, this value of j. Now, what happens if we increase j by 1? What do we get? All right? So now we say, all right, assume it's true for some value of j and let k equal j. All right, then we have A sub j equals P times 1 plus R over N to the j. That's true by assumption. Okay? And then we say, what happens when we increase j by 1? So now we let k equal j plus 1. And now we basically do what we were doing before, only this time without a concrete number, just the variable j plus 1. All right? Well, to find a of j plus 1, we said we have to take a of j and add to it I of j plus 1. Well, we know a of j because we said by assumption it must be true that it's this, so we substitute that in. We get p times 1 plus r over n to the j plus, now for I of j plus 1, we go back up to here, and we know that means that we subtract 1 from j plus 1 to get j, so we do a sub j, which again is just this right here, so it's just p times 1 plus r over n to the j, times what's left over in our I sub k, well that's r over n. And I'll just come on down here, make this a little bit easier, and I'll say, okay, what happens with this? Well, again, I've got something very similar in both of these. I've got p times 1 plus r over n to the j, I've got p times 1 plus r over n to the j, so I can factor that out, and this gives me then p times 1 plus r over n to the j times the leftovers. If I divide everything out of here, I'm left with 1. Divide almost everything out of here, what am I left with? I'm left with r over n. But what does that really mean? I've got this quantity being multiplied with itself j times, and then being multiplied with itself one more time. So it's really a total of j plus 1 times. So this is just p plus 1 plus r over n to the j plus 1. Which is exactly what we want if this is true. Because if this is true, then I plug in j plus 1 for k here, and plug in j plus 1 for k here, which is exactly what I got. So it works for the second case. So how do we put those two things together to show this is a proof by induction? Well, what I basically said with part 2, is that if it's true for some value of j, then it's always true for the next value of j. Always. Which means then it's true for the next one after that, and the next one after that, and the next one after that. Well, part 1 showed it is true for some value of j. It's true when it equals 1. So I know it works at 1, so it must work at 2. And since I know it works at 2, it must work at 3. I know it works at 3, it must work at 4, and 5, and 6, and 7, and all into infinity. All the natural numbers. So for any natural number k, this turns out to be true. And thus, this is our formula for compound interest. Now, to be fair, we're usually going to drop the subscript k, and we're going to rewrite k a little differently here. Because think about it. If I loan you money, and I'm compounding, let's be silly here, I'm going to compound 200 times per year. Okay? And you're going to keep the money for 5 years. That's a total of 1,000 compounding periods. Let's say you pay me back after 3 years, 2 months, and 24 days. How much money do you owe me? Well, which compounding period are we at? I have no idea. And unless I do a large spreadsheet with 1,000 entries, I'm not going to know. So I need my k to actually be in terms that better make sense. Well, we can see what it would be if we come back over to here. And we recognize that when we wrote this interest equation, we said that t equals 1 over n, because for each interest period, it's 1/nth of the year. Which means for each year, I have n compounding periods, which means in t years, I have nt compounding periods. And so really, we ultimately end up rewriting this where we just get rid of the subscript on this first one. That's just by convention. And we say the number of compounding periods k is actually n times t. In terms of numbers, I actually know, because I define n, and then t is how long you've kept the money. And there is our actual compound interest formula that we're going to use to fill in more spots on our chart. Okay, now that we have our formula for compound interest, a equals p times 1 plus r over n, all to the nt. It's a simple matter of just plugging in our values for p, r, n, and t to be able to fill in this chart here. Now, I first started by talking about what about being quarterly, and we said quarterly means there's n equals 4 compounding periods in a year. And so we plug in 4 for n, and then I plug in, of course, my original P and my original R, because those don't change. And then I just plug in 1, 2, 3, 4, and 5 for T into a calculator, round to the nearest penny, and I can fill in that chart really easily. So again, I leave that as an exercise for you to do to verify, but notice how much faster that will be versus doing each individual compounding period. Remember, that would be 4 times here, another 4 here, another 4 here. That'd be 20 to get down to here. Okay? And I could even go further than that and say, what if I earn my money monthly? That's how often I earn my interest, and I turn around and reinvest it. Well, that would mean n equals 12, assuming 12 equal months, of course. And so just plugging in 12 for n, and then plugging in 1 through 5 for t, I can very easily fill in the chart here and see the difference. Whether that's a realistic scenario or not doesn't matter. It's the fact that I can, in fact, calculate it. Now, here's what's really kind of interesting. In each case, across each year, it's always increasing. Okay? No matter how many years it is, I'm always increasing as I go across. So as I increase n, I'm always getting bigger. But notice at what rate I'm increasing. Here I jumped up by $25 when I doubled. If I doubled n again, here I didn't jump up by 25. In fact, I only jumped up by $13.13. Then here I tripled n, and I jumped up by $9. So I made n much, much, much bigger, and yet the amount that it increased became a lot smaller. And we can see that for each of these. Although I am always increasing, the rate at which I'm increasing seems to be getting smaller and smaller. And so we might go to the extreme with this. What if I earned interest daily? N equals 365. Or hourly? Ooh, n equals 365 times 24. Or minutely? N equals 365 times 24 times 60. Oh my gosh, keep going. Secondly, I earn interest every second. I wrote a computer algorithm that monitors the stock market trade and is just constantly, every second, making changes. And those changes average out to a 10% increase per year for me. But I'm earning interest every second, and I'm reinvesting that interest every second. So all of that interest is earning interest. That means I'm increasing as I keep going that way. What if I broke it down to milliseconds or microseconds or nanoseconds? What if I thought of time as just being this continuous line, which there is no smallest amount of time, and so that at any infinitesimally small point in time, I'm earning an interest and then reinvesting that interest. In other words, I'm continuously compounding that interest. Now, don't get uppity, you particle physics fans out there. I'm not talking about reality and the idea that there's probably a shortest amount of time called the Planck time. That's not what this is. This is a mathematical experiment, and in math, we can be continuous. We can be smaller than reality. So please do not leave me comments about that. I'm well aware of the existence of Planck time. We are not focusing on that here. If you didn't know what that was about, look it up. It's interesting. Okay, so that would be the next question. What would happen if I could compound continuously? That's actually going to be the subject of our next video. So remember, you watched it, you can't unwatch.